So now we will discuss deep latent variable models. So if we think about modeling in high-dimensional spaces, so this is a very difficult task. And why this is difficult? So we can look at these two images, right? So we have some handsome person and very beautiful horse. And now I can ask you a very simple question. What is the difference between these two images, right? So at the first glance, it's really hard to see, but if you stare at these images for, I don't know, a second, 2, 3 seconds, you immediately notice that, all right, there is a black dot in the middle of this image on the left. And this actually tells us a lot, namely that one single pixel or a small group of pixels, they don't contain a lot of information about the image. What is important is the structure, right? How these pixels formulate patterns, right? And so this simple example gives us a very good insight, right? That this modeling high-dimensional spaces could be very difficult. And mathematically speaking, we can say that we can imagine all possible dependencies among pixels. So go wild and think of any possible pattern, and we can even say that maybe there is an infinite number of these patterns, okay? And we denote these patterns by this psi. Somehow this psi is some kind of pattern that is applied to the whole image, right? Or some group of pixels, right? And this product could be enormous. It could be something like really even infinite, okay? This z is here for normalizing to have a distribution over pixels or images. And I use all these words like infinite or enormous on purpose because this will be very problematic to model, right? We can, you can, I can ask each of you, of course, right now it's impossible because I record this video without you, but if we are in a classroom, I could ask you every single person, we can come up with thousands of possible dependencies of pixels. And simply, it is, very hard to say how to model it, how to approach it, right? And a possible solution to it is to use latent variable models. So in other words, we can say that instead of working on the pixel space, we can try to extract some features that are useful, ideally learn these features, and then we will simply work in this lower dimensional space where there are predefined features, okay? Maybe very abstract features. And how to model it from this perspective, right? So we will think about the following generative process, very simple generative process. We'll first sample some latent variables, a code, and then for this given code, we will generate objects. So I'm now using pretty abstract words, but you can say that, all right, so we have faces of, images of faces, and we can say, well, what is the shape of a head, whether a person is bald or is hairy or blonde or black hair, glasses or no glasses, beard or no beard, gender, and so on. And you can say that this is our latent space, right? So this is our code Z. And now by sampling this code, I ask my decoder, some model, to actually generate for me this face, all right? Here we talk about something more abstract. Here we say about, we have some features that are continuous random variables, right? And let's say that in this case, we talk about the high dimensional space that is 3-dimensional and low dimensional space that is 2-dimensional, right? Codes are 2-dimensional, and what we want to do, we want to generate in three-dimensional space. Moreover, we can actually say, and if someone is interested in geometrical perspective, we can actually say that this two-dimensional space is a manifold that is embedded in this three-dimensional space. So in other words, imagine that you have a paper, and then this is like a plane, and then you say that, all right, now we can fold this paper, and it will be, it is now in 3D, right? This two-dimensional plane now is folded, and this is somehow in 3D, okay? And in other words, if we think of images, so a lot of images will be simply a crap. They will represent nothing. So we are looking for this manifold, this plane folded somehow in this pixel space that actually covers or somehow grasp this this part of this high dimensional space, pixel space, where real images lie. Okay. And so this could be visualized as follows. And now we can say that on this plane, on this paper, right, we define a distribution. All right. So we say that in some places, some points are more probable than the others. And once we have it, we can start generating from that. All right. So we take one point, and then we decode it back to the high dimensional space, right? So to pixel space. And we generate a horse, for instance. Then we take another point, we decode it, we generate a new image, and we take another point and we generate, and so on, so on. So I hope that now you get this idea. You see what is the generative process, right? In latent variable models. And one very good trick to check whether your model works properly, always think in this way. Think about a generative process. Think how to generate your object of interest. This is more a general trick, let's say, because you can take any probabilistic model, and if you factorize it in some sense, and you write down how you generate your data, then if you code it up, and if you, in your code, it is exactly the same generative process, then everything is fine. Also, if in your generative process you have some loops that, you know, you generate something, and then you generate something again that was generated before, it means that something is wrong. Okay. So this is latent variable model. This is the main idea. And of course, what we need to do, we need to think of the log likelihood function, right? So we told already during the first lecture that the log likelihood function is the most important quantity, because this is our objective function. This is our learning or training objective. So this is the probability, right, of observed data. And to obtain this quantity, we need to, of course, marginalize out or sum out all latent variables, right? So we apply here the product and sum rule. And because we are interested in taking logarithm, because it helps us with calculations, modification of probabilities. So we face this problem of calculating log of an integral, right? And how to train such model efficiently, because what does it mean, this integral here? This is actually the expected value with respect to z that is sampled from this marginal distribution P of z for this decoder, right, or generator, how we call it, is P of x given z. So of course, generating all possible points is infeasible. We can't do that, right? So first we will look at linear latent variable models. So we'll consider what if we take a model that is linear, right? So there's maybe a big jump from this slide to the next ones, but we are just thinking what we can do, right? And so first we say that we assume linear dependencies. Okay, what does it mean? It means that we take first a marginal distribution over z's over latent variables as standard Gaussian, right? So there is nothing fancy. Now we say that in order to generate an object in high-dimensional space, we transform this z by applying a linear transformation. So in other words, we just multiply it with some matrix W. We also add some shift. So we shift it somehow because these are from standard Gaussian. So maybe we want to shift this standard Gaussian and then transform it. And of course, we add some kind of noise to be stochastic, right? Because we want to generate in a stochastic manner. So now this noise is zero mean and some covariance matrix that has on diagonal the same variance, right? All right, so this is how we define our model. So we generate some low dimensional space, then we go to the higher dimensional space, and we transform it by applying some linear transformation. We know this is a deep learning course, so we can say that this is like applying a single linear layer in our in a neural network sense, right? So this is a bias, and we assume some linear transformation, linear layer. Then what we get the following distribution over X. So this is simply because this is standard Gaussian. So this is these two components, they constitute the mean value of this distribution, and then by adding this Gaussian random variable, so it gives us the covariance matrix. So how does it look like? So this is the generative process is the following. So we have this, let's say, one-dimensional problem. This is the low-dimensional space. High-dimensional space is two-dimensional. And we first generate some z, then we transform it to this, we transform it to this high-dimensional space. We shift it, right? And then also we will be somewhere generated in this region where the covariance matrix defines how we can spread this point, right? Somewhere around this mean. Okay, so this is the generative process. This is how it works. Now, of course, the question is how to calculate the log likelihood, right? Because we started with this question. And so we have a linear transformation, we have only Gaussian distributions. This is the decoder is Gaussian, or the generator, or how we want to call it. This conditional distribution is Gaussian, and this is Gaussian. All right. The beauty of Gaussians is that they are analytically tractable. And for instance, if we look into the Bishop's book and we read about marginal and conditional Gaussians, we can actually calculate the marginal distribution over X. Okay, so it turns out that this integral could be analytically calculated, and this gives us the following distribution. Okay, let's take a look at it. So it turns out that distribution over X's is a Gaussian distribution with mean given by mu, and now we have a complicated, more complex covariance matrix, right? So it's no longer diagonal. we have full covariance matrix, and it's determined by this linear transformation, right? This matrix W. And voila, we have a tractable integral. We can calculate it analytically. And now taking, of course, logarithm of p of x is taking logarithm of Gaussian, which is tractable, and we can calculate it. How it looks like, so before we got this generative process. So now it turns out that if we marginalize out over all these, right? So if we, for every single point we will take of z, calculate the distribution, it turns out that this will be such Gaussian, okay, centered around this mean, right? So this is a good news. And even further, it turns out that if the model is, the dependencies between random variables is linear, and all distributions are Gaussian, we can also calculate the posterior over the latent variables, C. So this is again a Gaussian. But now we have a little bit more complex distribution in the sense that we need to calculate something. So first of all, of course, we need to invert it. We need to go from z to x, right? So now we need to calculate, the mean is calculated in the following way, where m, we need to inverse it, calculate the inversion of M, matrix M. M is the covariance matrix from the previous slide, and it appears in the mean and also in the covariance matrix, right, for this distribution. And again, how we can calculate it, please take a look at Bishop's book, right, because he presented exactly the formula how to calculate it. We need to just write exactly, use our linear dependency. Right. So this is the final model, and this model is called probabilistic principal component analysis. All right, and it shares a lot of with just principal component analysis, right? But we will use this probabilistic or pPCA to extend it to non-linear dependencies, all right? But if we have linear dependency, you can say that if we have a single neural network with single linear layer, this is the principal component, probabilistic principal component analysis, all right? And in this one single slide, we have the marginal distribution over z's, we have a conditional distribution of x given z, so we can say that this is our decoder. We will use this nomenclature later. And we have also an encoder. So for given x, I can actually encode it in the latent space z, right, and go back. So you can say this is encoder, decoder, and marginal distribution over z's. And for all of them, we have Gaussian distributions, right? And we can also further calculate marginal distribution that we'll use for learning. All right, so let's take the logarithm of the likelihood function, right? We have n data points denoted by big matrix X. We assume that they are IID, so identically and independently distributed data. So we can turn this joint distribution, this likelihood function, into a product of points, that every single point is identically distributed. Since there is a product, so logarithm kicks this product out and turns it into the sum. And now, of course, we need to just consider a single Gaussian, right? And so everything is Gaussian, right? We keep it in mind. So now we can calculate it in the closed form, where the matrix C is given by this formula, and inversion could be also calculated in this form, right? What is the difference between M and C, let's go back. M is W transpose times W, but C is W times W transposed. Again, why this is different? Because multiplying matrix, rectangular matrix with rectangular matrix, the resulting size, shape of this weight matrices, these covariance matrices, it will be simply different. And C is for the high dimensional space, so for X, and M is for low dimensional space, so for Z. And why this is actually beneficial? Because inverting C now reduces to inverting M, that is just simply smaller. So if we want to calculate these inversions, so it will be easier. Complexity will be lower because we will just invert smaller matrix. All right. So it turns out that we can calculate the solution analytically, right? So of course we use the log likelihood function for training. This is our objective function, but we can actually sit down, we can take a pencil or a pen and a sheet of paper, and we can start calculating the solution. So what we are looking for, right? We are looking for W. This is our transformation. This is our linear transformation. I should have said that in the very beginning, actually, but this is what we are looking for. These are parameters, right, of this model. The next parameter is the mean, right? And so we are looking for these parameters, and we want to maximize the logarithm of the likelihood function, right? Or minimize the negative log likelihood function with respect to W and mu, and sigma, right, as well, so the noise. And it turns out that we can actually calculate it analytically, all right? So first thing is that what we need to do, we need to calculate the empirical mean. So this is this X bar. Then we need to calculate the sample covariance matrix. So calculate it's using standard tools. And then what we need to do, we need to calculate the eigen decomposition of this matrix, the sample covariance matrix, to obtain a matrix with eigenvectors and a diagonal matrix whose elements are eigenvalues for this sample covariance matrix. And these matrices U and L, they should resemble the principal component analysis. I see that there is a mistake here because it should be M times N, if I'm not mistaken. Or D times D, actually. Let me think about it. Yeah, I think that I need to check this, but this is not necessarily correct, I think. Right. There's also matrix R, but we'll discuss this R in a second. This is a rotation matrix because these Gaussians, you can rotate them arbitrarily, and this is just rotating these values, so they don't change much. And how to calculate this variance? It turns out that this is just simply taking the average variance of discarded dimensions. So of course W is D times M, where D is the high dimensional space, M is the low dimensional space. So we just, if we take M, for instance, let's say D is 100, and if we take M 60, so we need to take 40 dimensions with lowest eigenvalue, and we just need to calculate average of this, and this will be the remaining variance, average variance of discarded dimensions. Okay, and R, as I said, is an orthogonal matrix. Orthogonal matrix, you can think of rotations. So for instance, rotation is an orthogonal matrix. reflection could be also described by orthogonal matrix. Right. So if we use the eigendecomposition of the sample covariance matrix, then we can simply take R equal identity matrix. Identity matrix is also an orthogonal matrix. And the definition of orthogonal matrix is that if we take orthogonal matrix, for instance, R times R transposed or R transposed times R, this should give us identity matrix. All right. So if we calculate everything analytically, we should end up with a simple solution that is simply R equals identity, the identity matrix. However, in practice, the complexity of the eigendecomposition is d to the power of 3. So we have this cubic complexity. So then the complexity of calculating covariance matrix is n, so number of points, times d squared, right? Squared. So you see that for high dimensional problems, this will be a big issue, right? So, or for many points, this could be simply intractable. So for, let's say, large problems like dimensions are more than 1,000 dimensions, more than 1,000 points, or I know 10,000 points, that it will not easily fit to the memory of our computers. We can use two numerical methods. Expectation maximization. You are maybe familiar from machine learning course about this technique, or we can just simply use gradient-based optimization, right? So since we are in this course, so we can think of the pPCA as a single layered neural network with only a linear transformation, linear layer, and you just use PyTorch to train these weights for this objective function on the previous slide, just using SGD or Adam or whatever. However, then you need to be aware that this orthogonal matrix could be actually arbitrary. So it means that there is no unique solution. So if two people run the same algorithm, the same model on the same data, you can get, due to stochasticity and stochastic gradient descent, you can get totally different results. So you cannot simply compare them. They are the same up to the orthogonal matrix, some R. And how this probabilistic PCA works. So let's say that we can actually use them for reconstruction. So let's say this is our original image. We have trained pPCA. And if we take a pPCA with only one component, and you want to reconstruct, so calculate this P of X given Z. So first you can say that, all right, I go from X to Z. So I calculate this P of Z given X. I sample one point in this space, then I'm going back. So this is the reconstruction you get. So this is probably some kind of average digit tree that will be given for almost all different kind of trees. Then if we take more components, so you see that actually it starts resembling this digit. If we take 50 components, we are almost there, right? We still have some artifacts, but this is pretty similar. And if we take 250 components, and when, let's say, this original image is 784, we get almost ideal reconstruction with some small artifacts. And also to see how this pPCA works, so we can also think of projecting, for instance, two-dimensional data on one-dimensional space. So again, this is like a manifold. We just project it on this manifold. Okay, and why they are off? Because we have some variance there, right? So some uncertainty. All right. What are advantages of pPCA. We have an exact likelihood, we have analytical solution up to some reasonable dimensions or problems. We have posterior over Z in an analytical form. So you can, what does it mean? It means that you can sit down, you can code it up very easily. You can just take these slides, you can write these slides down, and you have everything. It allows compression, as we've seen, and it allows to generate new points. However, of course, we have linear transformation, so it drastically limits the applicability of these models, right? So, or this model. We cannot use them to any data. It will work only for very simplistic data. Moreover, for more complex data, it will require a lot of components. So M will be close to D actually to work well. And unfortunately, this doesn't work for binary data. It works only for continuous data. All right. How we can improve on that?